This video is about organometallic complexes, and in particular it's about their electron counts and the rules for counting electrons. Because of the fact that organometallic complexes are those that have metal-carbon bonds, we're dealing with ligands that are usually strong sigma donors. And even in the case when they're not strong sigma donors, they are typically pi accepting. And so in these organometallic complexes, we're typically dealing with strong field ligands. And this means that organometallic complexes often have large delta or large d orbital splitting. Now, if we have organometallic complexes that have strong field ligands and large delta values, this leads to a strong preference for two types of geometry, the octahedral geometry or the square planar geometry. Because these organometallic complexes have large delta values, it turns out that complexes with 18 electrons in the case of octahedrons or 16 electrons in the case of a square plane are especially stable. And so this is known as the 18 electron rule. We can explain the stability of 18 or 16 electron complexes with molecular orbital theory. So let's look at the d orbital splitting for a metal ion under an octahedral ligand field. I'm first going to focus on the octahedral case, and I'm going to construct a quick and dirty octahedral molecular orbital diagram. So on the left here, I've shown my metal atomic orbitals with the symmetry labels under an octahedral field, and I'm showing my 6 ligand salx here on the right-hand side, and I'm going to just construct a diagram based on 6 sigma only 2 electron donors. I've colored my bonding orbitals in green, my non-bonding orbital in blue, and my antibonding orbitals in red. And here is what we typically think of as the d orbital splitting for an octahedron, where this is your delta O. But if you look at the number of orbitals here, the molecular orbitals that are not antibonding, and you try to fill them with electrons, you'll notice there are 9 orbitals, and to fill these up without putting anything in the e.g. star set, this gives you a total electron count of 18. So because we have 9 orbitals that are either bonding or non-bonding, having more than 18 electrons would force us to put electrons into antibonding orbitals. So having more than 18 electrons would be unfavorable. Having 18 electrons in this case is stable, but remember, this is the case I've shown here for a sigma only case, so like the ligands are sigma only donors. So now I'd like you to recall the discussion on how pi accepting ligands affect the value of delta, and you hopefully can remember that pi acceptors actually increase this delta because they actually lower the energy of this T2 set and make it bonding. So because a lot of the times when we have these organometallic complexes, we're actually dealing with strong field ligands, and a lot of the times they're actually pi accepting ligands, the T2G becomes bonding, and that's even better. And so then you're filling up 18 electrons in all of the bonding orbitals. And anything more than that, you're basically going to antibonding and you're lowering the ligand field stabilization energy. But again, 18 electrons is the kind of magic number in octahedral complexes because that's the number of electrons that maximizes the stability of the complex by filling up all of the bonding orbitals. So once again, I've drawn here a case for sigma-only ligands. You can imagine if it were a pi-accepting ligand that you would lower the energy of this T2G, but if you want to see that example, you can look at figure 22.1 in your textbook. The 16 electron rule can also be explained with molecular orbital theory. So I'm going to construct a quick and dirty molecular orbital diagram for a square planar compound where my ligands, again, are sigma donors. So again, on the left-hand side here, you can see my metal atomic orbitals, those valence orbitals that are going to interact with the ligands, and the symmetry labels that are associated with a square planar complex from the D4H character table. And then on the right-hand side, I have my ligand salx. So I've written my molecular orbitals in the center here. Again, my bonding, the ones with the most bonding character are green. The ones that are kind of non-bonding in character are blue. And my anti-bonding orbitals are in red. I will put a box around my square planar d orbital splitting. So this is the kind of shortcut that I usually draw, where I have 2 orbitals and then 3 single non-degenerate orbitals. Now, if you count the number of electrons that aren't, basically here's your cutoff, because after you add more electrons past this level, you're putting them into the anti-bonding B1G. So that gives you 8 orbitals, which would allow you to fill up this metal complex with 16 electrons before filling any of the anti-bonding orbitals. So hopefully you can see how molecular orbital theory allows us to explain the observation that 16 and 18 electron complexes are especially stable. Now, if you know the number of electrons that are in the valence shell of a metal ion, you can predict its reactivity. And so it's useful to know how to count the electrons. There's no right way to do this. And there are 2 kind of systematic methods that exist. The first is the neutral ligand method, and the second is the donor pair method. They both have their advantages and disadvantages, and you can read about those in your textbook or in the supplemental reading that I gave you. I'm going to be consistent with your Shriver and Atkins textbook, and I'm going to use the donor pair method, and I'm going to explain that here. I'm not going to cover the neutral ligand method. I prefer the donor pair method because it allows you to calculate the oxidation state of the metal, and you need to know that information to understand what kind of reactions are happening in a catalytic cycle, and you also need to know the metal oxidation state so that you know the number of d electrons in the metal. So the donor pair method is my preferred method because it's the most efficient way to get the information that I need to know. The other advantage is actually that I can just use my chemical intuition to predict how many electrons each ligand is going to donate to the metal ion. So I don't need to memorize a list of ligands and what number of electrons they're donating or what their charges are. I can just use Lewis structures to understand things without memorizing a table. So this donor pair method is also called the closed shell or oxidation state method. And I'm going to first use the example of an organic molecule that you're familiar with to show you how you would do this. So I'm going to use carbon dioxide as my example. So the first step in this is to identify the central atom and the ligand. So here my central atom is carbon and my ligand atoms would be oxygen. I'm going to remove those ligands from the central atom as if they were full octet species. So that means I'm going to remove the oxygen with a full octet. In the case of oxygen, I know that oxygen by itself would be O2 minus. And so I'm essentially taking the oxygens away with their electrons from the carbon. And I'm drawing these Lewis structures kind of funny, but I'm showing you that basically the electrons in these double bonds are coming out and they're staying with the oxygen. So it looks like a funny Lewis structure. But I'm doing that to show you that it's being removed with those electrons from the carbon-oxygen interaction. This leaves the central atom with no electrons around it. And so this would be carbon 4 plus, and then the oxygens would be 2 minus. When I'm doing this, I implicitly did this. I didn't explain it. But so once you remove the ligands from the central atom, of course, you're going to also assign oxidation states to the ligands. So if I have an oxygen with 8 electrons around it, I know that that's a 2 minus. And I'm going to also assign oxidation states to the central atom or the metal. And in this case, the carbon without any electrons around it is a 4 plus oxidation state. So that takes care of step 1. So if I know the oxidation state of the central atom, I know how many electrons it already has. And in this case, it doesn't have any. And I now need to basically figure out how many electrons each of the ligands is contributing. So I count electrons in each bond as a 2-electron donor. Since carbon doesn't have any electrons on it, I can basically ignore that, and I can just count the electrons in the bond. So each of these ligands is going to be donating 4 electrons. And what that means is that this would be an 8-electron species. And so we can see that this carbon dioxide obeys what we know as the octet rule. So let's look at a metal complex. Well, this would be a bromo-pentacarbonyl manganese complex. And if I want to count the number of electrons by the donor pair method, I'm going to do the first step, which is to basically remove the ligands as closed electron species. And so for the carbonyl ligands, I know that that means that each of the carbons has 2 electrons that actually came from this initial bond. And the bromide also has, it will take with it the electrons. So as a closed species now, I have 8 electrons around each carbon and 8 electrons around the bromide. Now I'm going to calculate the oxidation states of each of these ligands. The carbonyl ligands are neutral and the bromide has a -1. And now to balance the charge here, I'm going to calculate the oxidation state on the manganese. So it has to be +1. And I didn't explicitly state this, but the charge on this entire complex is 0. So that's why I can balance the charge like that. So now I know that I have a manganese +1. And now I should count my the number of electrons in manganese +1. I know that this is a D6, and this is important information. So now I'm going to count my electrons, my total electrons here. I'm going to count each of these bonds as a 2-electron donor. So each of the carbonyls is going to donate 2 electrons, and the bromide is going to donate 2 electrons to the metal. So I have 6 sigma bonds, 2 electrons each, gives me 12 electrons from the ligands. And then the number of electrons that were already on the metal complex was 6. I knew that from the oxidation state of the metal. And so my total electron count for this complex is 18 electrons. So this is the donor pair method. Again, the advantage is that you calculate the oxidation state of the metal ion, and that can help you later on, especially with the catalytic cycles and or understanding phenomena based on the d electron count. You want to be able to identify the types of ligands. There are the X-type ligands, and these are things that have negative charges on them. So they're anionic by themselves, and they're typically 2-electron donors. So things like bromine, H-, OH-, these are anionic, and they're 2-electron donors. There are L-type ligands, and these things are the neutral 2-electron donors like amines, waters, or ethers, or alcohols, and things like trialkyl phosphines. These are the neutral 2-electron donors. And there are things that are neither or both. So something like the cyclopentadienyl anion, which is often represented as CP star. This particular guy can bind in several ways. It depends on how it's coordinated to the metal. You have your 801 case where it's acting as a sigma donor, like any carbanion would. So this is a 2-electron donor with a negative charge. You have the eta5 case here, and that's where it's basically a metal pi interaction, where you think of the resonance hybrid. You know, this still has a negative charge overall, or the cyclopentadienyl anion still has a negative charge overall. So in this case, however, it's actually a 6-electron donor with that negative charge. Now, it's pretty easy to see why it's a 6-electron donor if you remember that it's the pi system that's interacting with the metal ion here. And just count the electrons in the pi system. There's 2 in the lone pair, there's 2 in each of those 2 double bonds, and so that's a total of 6 electrons. And this thing can also act as an eta-3 donor, and that's where you basically have, it's kind of like an allylic anion, so you have basically one of the double bonds and the anion, or the lone pair, kind of a resonance hybrid there, donating into the metal ion. And in this case, you're basically leaving one of the pi bonds out of it. And so this is a 4 electron donor with, again, a 1- charge. And then you can also have bridging ligands. And in the case of a bridging X ligand, so you have, again, X is the anionic 2 electron donors. So something like a Br- or a Cl- can act as a bridging ligand between 2 metal ions. When it does that, it counts as a regular X ligand, so with a negative charge and a 2 electron donor for one of the metals, and it counts as an L ligand, or a neutral 2 electron donor for the other. So if we kind of dissect this system here, if you remove the first metal, or you remove the ligand from the first metal, let's say then you're removing that as an L-type ligand, so this is a neutral 2 electron donor, but then when you remove the X group from the other metal, now this has a -1 charge on it, and so it's acting as an X-type ligand for that second metal ion. So with this information, you should be able to solve problems that involve counting electrons. I'd like to apply this now to a catalytic cycle. The Monsanto acetic acid synthesis is an important industrial synthesis that's been used since 1971. It essentially just takes methanol and carbon monoxide, and in the presence of a rhodium catalyst and hydrogen iodide, you will get acetic acid. It looks like an organic reaction, but it can also be classified as an organometallic reaction because this rhodium catalyst is actually an organometallic complex. Now I'm going to write the catalytic cycle below. So here I've written the catalytic cycle for this reaction. So you take this square planar rhodium complex, it's a diiodo dicarbonyl rhodium, and when you add methanol and hydrogen iodide, or when you combine methanol and hydrogen iodide, it gives you methyl iodide. This reacts with the square planar complex. You now got a new carbon rhodium bond and a new iodide rhodium bond. This reacts to form this kind of complex. And then in another step, carbon monoxide is added. You actually add a new carbon monoxide ligand there. And in the last step, you eliminate this molecule and reform your square planar rhodium complex, and then this molecule reacts with water to give you the carboxylic acid. So that's the catalytic cycle. Don't memorize catalytic cycles. I want you to be able to look at them and understand them. And right now what I'd like to focus on is just what's happening to the metal complex in each one of these steps. So the first thing you can do when you're looking at the catalytic cycle, it's helpful to calculate d electron counts and total electron counts. So understanding the oxidation state of the metal complex lets you know its d electron count, and then you can count its total electrons. So here I've got a rhodium-1, which is a D8 metal complex. So that is consistent with the fact that it's a square planar complex. So I have 8 electrons from the metal. I have 2 electrons from each one of the 4 bonds. And so this is a 16 electron complex. In the next metal complex here, I have a rhodium-3, which is D6. And once again, I have all of these things are 2 electron donors. And so I actually have 2, 4, 6, 8, 10, 12 electrons from each of the bonds. So 6 plus 12 is 18. This is an 18 electron complex. The complex at the bottom of my cycle is again a rhodium-3, and it is a 16 electron complex. And my last metal complex here is again a rhodium-3, and it is an 18 electron complex. So you should have calculated those things already in one of your homework assignments. The oxidation states of the metals tell me something about what's happening here. The first step in this reaction, you are going from a rhodium-1 to rhodium-3. So you're oxidizing the metal. And this step is oxidative. You're also adding something to the metal, and it's actually, this step is called an oxidative addition. So in the first step, you're oxidatively adding methyl iodide, and you're at the same time breaking that carbon iodide bond, going to a rhodium-3 18 electron complex. So you're adding some ligands here, you're adding electrons, and you're going from a square planar to an octahedral complex. It's very common for 16 electron complexes to go through addition reactions, and you also know this from what we talked about with mechanisms. You know that square planars usually go through associative type mechanisms. So this is consistent with what we've learned so far. I'm going to talk about this oxidative addition and the opposite of the oxidative addition. So over here, in my last step here, I'm going from a rhodium-3 18 electron complex to a rhodium-1 D8 complex at the same time as I'm eliminating something. This is the opposite of oxidative addition, and it's reductive because you're reducing rhodium-3 to rhodium-1, and it's reductive elimination because you're eliminating something from the molecule. You're eliminating electrons as well. You're going from an 18 electron octahedral complex to a 16 electron square planar complex while eliminating, in this case, the product or one of the precursors of the product for this cycle. In the other reactions, we're not actually changing oxidation state, so these are not going to be reductive or oxidative. The reaction here, in this reaction, what's happening is you're actually sliding this one of these carbonyl ligands into this bond. And at the same time, iodine is swinging up to take the place of one of these equatorial ligands. And so in this product down here, I actually haven't colored the iodine red because the red iodine could be any one of these three. But when this carbonyl slips in between the rhodium carbon bond here, this step is a carbonyl insertion, or it can also be called an alkyl migration. Another name is a 1,1 insertion. In this product here, now you've got a vacant site, and it's really easy for something to now add to this complex, and that's what happens next. So here you simply just add a ligand, and this is simply just called ligand addition. From knowing the oxidation states of the metal and the total electron count, we can name the steps in the catalytic cycle. And this should follow logic. Your square planar complexes will typically add a ligand. In this case, it's an oxidative addition. Then the next thing to happen is either going to have to be an elimination or some kind of reduction in the coordination number. So you have to change the coordination number to a lower number in order for the cycle to continue. And this is accomplished through a carbonyl insertion or an alkyl migration here. Now you're left with a 5-coordinate complex, which is a 16 electron complex. And again, 16 electron complexes, just like the regular square planar, if it's 16 electrons, that means it will probably add another electron pair somehow. And so this is accomplished in the next step through a ligand addition. Now you're at an 18 electron complex. Once again, you need to eliminate something for any reaction to happen, because octahedral complexes typically are dissociative types of reactions. And so here this is accomplished through a reductive elimination to give you your initial catalytic organometallic complex and a precursor to the product. So again, when you look at catalytic cycles, I want you to be able to tell me the oxidation state of the metal, because that's helpful in naming the types of reactions, and the total electron count will tell you something about what next steps are possible. And so the next thing I want to do is talk about the types of reactions that you'll see in these catalytic cycles. And let me just start by saying that we're going to talk about some of the most common types of reactions, and this is far from an exhaustive coverage of this. You could take an entire course in organometallic reactions and their mechanisms. But again, we're just going to cover this very briefly. So let's start with oxidative addition and reductive elimination. And we're going to apply the principle of microscopic reversibility and say these things are really just opposites of one another. So when you take a metal ligand complex and you add something like this XY general molecule, what you're doing is you're breaking the XY bond and you're making a new metal X bond and a new metal Y bond. This is oxidative addition. And the opposite, where you eliminate two things from the metal and form a new bond between those things, is called a reductive elimination. So now I'll just list these things. So in the forward reaction as shown above, the oxidative addition, in this reaction, you'll know it when you see it because you're cleaving this XY bond, you're increasing the metal coordination number by 2, and you're also increasing the metal oxidation state by 2. And so we saw this, an example of this above, where rhodium-1 was converted into rhodium-3. So you're increasing the oxidation number of the metal ion by 2. Another example of this is the Grignard reaction. You may have learned in organic chemistry that the magnesium inserts itself between a metal halogen bond in this kind of way. In this reaction, you're increasing the coordination number of the metal by 2, and you're also increasing the oxidation state because in the complex this is a magnesium 2+. So once again, the reductive elimination is exactly the opposite of oxidative addition. They are microscopically reversible reactions, and in reductive elimination you make an XY bond, you decrease the metal coordination number by 2, and you also decrease the metal oxidation state by 2. Here's an example of a palladium complex which is going through a reductive elimination to give a new carbon-carbon bond and a palladium L2 complex. This is palladium 2 and this is palladium 0. And this product is a 12 electron species. It's not stable, so it will immediately react to form a 16 electron species. So now I'm going to move on to the carbonyl insertion, or I'm going to call it the 1,1 migratory insertion. So this is called a carbonyl insertion or an alkyl migration, and overall the result is the same. These actually mean kind of two different things. So I'll show you two pictures where an insertion and a migration can be defined slightly differently. If it's a migration, that means that X migrates, or an X would be an alkyl group. And if that's the case, that means that the X moves to the carbonyl. And so you would get something like this. If it's a carbonyl insertion, that means that the carbonyl actually inserts between the metal X bond. And there are experiments that you can use to distinguish these types of things, but overall, typically the results are the same. In this reaction, you're decreasing the metal coordination number by 1. You're decreasing the total electron count by 2, but you're not changing the metal oxidation state. The last two reactions are again an example of microscopic reversibility. A 1,2 insertion can also be called a beta insertion, and the beta elimination can also be called a 1,2 elimination. So for a 1,2 insertion or a beta insertion to happen, the two ligands that are going to interact must be cis to each other in the metal complex, and they must be syn coplanar. This goes through a concerted one-step reaction that involves a 4-centered transition state. And basically, you make a new X carbon bond as you break the metal X bond and you break one of the carbon-carbon pi bonds. So for this 1,2 insertion to happen, you are working with, so this X group can be some kind, either H minus or C minus phenyl anions also work, but you also need to have either an alkene or an alkyne in the cis syncoplanar position. The characteristics of the 1,2 insertion are that you decrease the electron count of the metal complex by 2. You add an X bond to the alkene or the alkyne. So now you've converted this, you basically added MX across this double bond, or it could be a triple bond, but you don't change the metal oxidation number. Now, beta elimination is the microscopic reverse of 1,2 insertion. So you're increasing the electron count by 2, you're eliminating X to form an alkene or an alkyne. And so you're going to be making a new metal X bond, and that's why you're increasing the electron count by 2. And you're, again, not changing the metal oxidation state. So those are all of the reactions I want you to know about. Again, when I show you a catalytic cycle, I don't want you to memorize anything. I want you to be able to tell me the oxidation state of the metal, the total electron count, and I want you to be able to identify these types of reactions based on the features that you see in front of you. The best way to learn this information is just through practice at analyzing catalytic cycles and even predicting catalytic cycles.